Alright, so this will be the last video for chapter 11. So it's kind of a shorter chapter. And just as an FYI, I have changed a little bit how I am writing on my iPad for these videos because my previous software broke. So if you see anything weird, right, you can probably see this pointer along with my laser pointer. Maybe it'll be fixed in the future, maybe not. Nothing in life is perfect. So let me know if there's any weird errors you see as they crop up. But for now, it should hopefully mostly be the same with a few of these weird additions. Anyway, so this last chapter, or portion of chapter 11, is about alcohols as leaving groups. And so what we're going to see here is some ways we can do some transformations with alcohols rather than as leaving groups rather than like what we've seen so far with oxidizing them, right? And so we're going to start with a quick review, right? We've seen some things already where we can have alcohols be leaving groups, right? For example, with this, right, SN1 conditions, right? Where we can have an alcohol, right, that gets protonated, right? We have OH here, plus HBr. We generate a hydronium ion, which leaves right on its own to get our carbocation, and then for the final step, right, we have HBr or nucleophile come in and attack that carbocation center, right, to get to our product here. So these SN1 conditions, right, some sort of polar protic solvent is probably also needed. Right, it's one way to have alcohol leave as a leaving group. Another way, right, is something we've already talked about, right, having, back in that chapter 10 videos, right, having our alcohols, right, attack these really good leaving groups, right, or making alcohol a really good leaving group, right, in this very simple sort of SN2 reaction where it attacks the sulfur. Right, we have one of our double bonded oxygens kind of break apart and come back together, and chlorine leaves as a leaving group, right, in order to make our oxygen here right now a good leaving group, right? And from here, right, we can do any sort of leaving group reactions, right, such as, again, right, Br minus or something. Another way to have alcohol leave as a leaving group, like as we discussed in chapter 7, is with this sort of E1 elimination, right? Having alcohol and exposing it to acid and eliminating H2, right? We're dehydrating an alcohol. So very similar to the last SN1 reaction, we have OH becoming OH2 plus, right, when we have it reacting with acid here, and then, right, it leaves on its own, right, to generate our carbocation, which can do resonance, so it's pretty stable, and then we have something come in, water, for example, and grab one of these protons to make our alkene, right, which is another way to make alcohol leave as a leaving group. So now let's look at a couple other examples. So without using any of these other conditions, we have a couple different ways we can do this. So one way is with something called thionyl chloride. So we have double bonded oxygen to that sulfur and these two chlorines here. And so what happens with this first reaction is we have our OH. We'll do the mechanism for a couple of these, okay? We have the OH come through and attack our thionyl chloride, and our end result is our chlorine here. But let's look at the mechanism, okay? So we have this come through and attack our thionyl chloride here, and I'll switch to using red. Right, it's going to come and attack, open up this sulfur oxygen bond here, and we get the following. Right, sort of similar to that tetrahedral intermediate we were discussing in a previous chapter, where we have a lot going on now. And so what's going to happen is this negatively charged oxygen is going to come down, right, and it's actually going to break off a chlorine. Right, so now we're back to our double bond oxygen here, still have a chlorine left over, positively charged O minus here. And so what's going to happen is a couple things, right? This chlorine, this other chlorine here, is going to come through, right? The chlorine group that left is going to come through and grab a hydrogen, right, to neutralize this. So we have, right, HCl over here, and then we have double bonded sulfur, this chlorine. And what happens next is a little funky, but this chlorine that's already attached to the sulfur is going to come through. Right, it's kind of long, so it kind of bends in on itself and attack that carbon here. And then this bond to oxygen is going to come to that sulfur. Right, and the products here, and the reason why this works, right, again, is this new chlorine bond, but we also have sulfur dioxide leaving, which is a gas, okay? And so when we have a gas leave, that really propels a reaction forward because it can't go backwards now. So even though, right, it's kind of a funky mechanism, right, the chlorine, right, is coming through and attacking here, the oxygen, right, is kind of wrapping in on itself to attack the sulfur, and we end up getting this side product, right, this disulfide, or this dioxide group leaving, right, again as a gas. Another example is with PBr3, and we get the same sort of result, where that oxygen has essentially just been replaced with a bromine. Okay, and the reaction mechanism is similar. Sorry about that. So let's look at the mechanism for this PBr3. Okay, similar to what we've seen already so far. Now, because you got to erase some of this to give myself more room, so I might have to write this on a different page. Just the nature of the B subwriting mechanisms, right? Sometimes things get a little wild. So for the mechanism for this, what does this look like? So we have our OH again. This time, right, we're attacking PBr3. So this OH is going to come in. I'll do this in red to make things apparent. Attacking the phosphorus. And so what happens here, and I'll actually draw all these bonds, is we have one of these bromines leaving actually on their own, or after getting attacked, right? So the end result for this, right, Br leaves, is the following. Right, similar to what we've already just seen, right? We have OH plus, and then we have this phosphorus group, right, attached here, two bromines, and then we have Br minus now coming through, and it'll actually attack the backside of this carbon-oxygen bond here. And so what's happening, right? Why are these transformations occurring? Mostly because, right, we're making oxygen a good leaving group, right? It happened in the last example too. It's gone from something that's not a great leaving group, similar, right, to adding to those tosyl groups. We're making alcohol a better leaving group, which is essentially all this mechanism is doing, right? Again, to generate bromine, and then we have our sort of phosphorus, side product here, right? And so for the final reaction here with inorganic phosphorus and iodine, I'll kind of write this off to the side. We don't need to know the mechanism here in this case. I've lost this somehow. This is just adding iodine. And the mechanism is actually similar to PBr3, but with inorganic phosphorus and iodine, we actually make Pi3 in situ, meaning in a reaction solution it's making phosphorus triiodine. Because this is actually unstable on its own, so if you can make it in a reaction solution, it's better than buying it commercially and then using it. Okay, so again, we're using conditions, right, to do things we've already seen. right? Because didn't we already see HBr do this fine, right? Take an alcohol, we do an SN1, and then we get bromine here, right? Haven't we already seen that? So we'll talk about this more in class about why we need to use different conditions. But again, if it doesn't work one way, right? If we can't use HBr on its own, and I encourage you to think about why, right? Why can't we use HBr on this, right? Why can't we just use HBr on this alcohol to get a bromine here? And we'll talk about this in class. Having different ways to do reactions is better, okay? So, something else we'll discuss during class is something called the Pinakoff rearrangement. Right, you can see, right, we have this sort of, right, E1 conditions, right? We know we're doing some sort of dehydration, but now we have a ketone as the end product, right? And we're starting with a diol, right, 2 alcohols. So we'll do this in class together, but let's try to think about what this mechanism looks like. Why are we getting here from here? And notice it seems like methyl groups have shifted as well, which we know can happen during these carbocation generations. So we'll take a look at this together in class in terms of doing this mechanism, okay? But see if you can do it on your own, because we'll kind of start off that way in our next class.